Assalamu alaikum everyone. Welcome back to our discussion on wind turbine energy. So we discussed about the Betz limit in the last class. What we want to do today is to basically uh, look at the definition for angular velocity, the turbine tip speed, and then again have a quick look at this graph which we already discussed. Now, angular velocity simply talks about the angular speed at which the turbine blades are rotating. So basically, it's the angular distance in terms of radians that are traveled per revolution, and for every revolution of the turbine blade, basically, if you're looking at a turbine rotor here. So one blade, second, third blade. So basically, when we talk about each revolution of this turbine blade, so one complete revolution for this turbine blade. So in each complete revolution, it is traveling an angular distance of 360 degrees, or simply 2 pi radian. So this distance is the angle it is covering, and then multiplied by the number of such revolutions it does per minute, right, in RPM. So which is n dot given here. So 2 pi times n dot, the angle covered times the number angles covered per number of rotations per minute gives us the angular velocity in terms of angles per minute or angles per second that is covered. Okay. Now the other thing that we need to calculate, or that's also very commonly used, is the tip speed. What is the speed at the tip of a turbine blade? So we want to find out how quickly this tip is moving around. And so the tip speed is simply the distance traveled by the tip in each revolution, which would be equal to the circumference of the circle formed by the turbine blade. So it will be 2 pi r times the number of revolutions per minute, n dot. So 2 pi r times n dot can also be written as pi d n dot, as shown here, pi d n. Or you could simply look at 2 pi r n dot and say, well, 2 pi n dot is simply the omega. So 2 pi r n dot would simply be omega r, right? Which is another way of writing the tip speed based on the angular velocity. Now, here we have plotted the efficiency of different wind turbines versus the turbine blade tip speed normalized by the wind speed, right? So omega r divided by v. So this is normalized to the inlet wind speed, and it makes sense to normalize it to the inlet wind speed simply because, well, if the inlet wind speed is higher, generally the tip speed of the would be higher, right? So you want to normalize it to make sure you're doing a fair comparison. Now, ideally, if the turbine was operating at the ideal situation, then the Betz limit is 0.5926. It's this dash line shown at the top. However, if you're having different types of turbines, then of course each turbine has its own efficiency curve, and you can see it peaks at some desired efficiency and then it goes down, right? Now, ideally, you want to pick a turbine design which has the flattest curve possible for a wind turbine design. And therefore, when we compare different turbine designs here, not the ideal one, right, the actual ones, then what we can see is this horizontal axis wind turbine, which is shown here, has a almost flat curve here, right, efficiency curve. And therefore, these are the most popular wind turbines that you can see around. Okay. Now, moving on, let's talk about what are the main reasons why we are not able to achieve the Betz limit, right? Betz limit of 59.26% wind turbine efficiency. Why are we not reaching that? Several reasons for this. The three most important reasons are: first, there's a lot of rotation of the wake behind the rotor swirl. So this is the rotor is the rotating part of the wind turbine, and there is going to be wake behind the wind turbine, as you can see here in this picture. So because of this, there's going to be efficiency losses. And this is going to cause efficiency losses not only to the first wind turbine that's in the series, but also you can see because of the presence of this wind turbine, the turbines behind this wind turbine are having different velocities. I mean, and they're facing different kind of a wind. So their efficiency in extracting that wind speed is going to be different. Okay. Second thing is, of course, we cannot have infinite number of rotor blades. So we have a finite number of rotor blades, and each blade has its own tip losses, which we cannot make zero, right? There will be some tip losses. And then certainly the last part is the non-zero aerodynamics drag that you have in the rotor blade, which is not just frictional drag, but also the induced drag. So these are three main aerodynamic reasons why we have we don't really reach the batch limit, right? There are other reasons as well, such as the mechanical losses due to friction on the shaft, and also the other losses within the gearbox, generator, electrical losses, and others. So all of this end up reducing the overall wind turbine efficiency. And when we calculate the overall wind turbine efficiency, as we discussed in the last class, is going to be the efficiency of the wind turbine multiplied by the efficiency of the gearbox slash generator setup. So we uh, narrow down all the inefficiencies into these two big boxes, and then the efficiency of the wind turbine takes care of everything that's involved in converting the kinetic energy of the wind into the energy of the shaft, the rotational energy of the shaft, and then the gearbox or slash the generator takes care of all the energy losses in converting the rotational energy of the shaft onto the electrical energy. Okay, so this are with this, with the overall wind turbine efficiency, we will take care of all the possible losses and give us the actual numbers in terms of how much energy is available in the wind and how much of it are we able to convert into electricity. Okay, so that's about it for the bets limit and the losses that allow us that basically because of which we are not able to reach the bets limit efficiency. Now let's do a very simple example for calculating the efficiency of a wind turbine. We have been provided with a wind turbine of 50-meter diameter rotor, and it's rotating at 25 RPM. This is the rotational speeds under steady winds with average speed of 10 meter per second. So the average velocity of the winds is given as 10 meter per second. Okay. Now the electrical output from this turbine is 375 kilowatt, and the combined efficiency of the gearbox generator is 90%. Now this efficiency is usually large. It's 90 to 92%. And this is given as 90% here. We can take the density of air to be 1.2 kilogram per meter cube. For all of this information that is given to us, we need to do a few calculations. The first part is we need to calculate the wind turbine efficiency. Okay. Now, wind turbine efficiency simply talks about the efficiency of converting the kinetic energy of the wind to rotational energy of the shaft, right? So here, basically, we're talking about how much energy are we able to get at the shaft of the wind turbine divided by how much was available. Now, how much was available? Well, we can calculate that very easily using the formula half rho a v cube, as we discussed before. Now, here the density is provided to us. The area can be calculated because we have the diameter given here. The velocity v cube is the velocity of the wind. It is also given as 10 meter per second. So the bottom part can be calculated once we calculate the area. Now the power output of the shaft or the rate of work output of the shaft is actually not given to us directly. It is given to us indirectly. Okay. How is it given to us? Well, it's given to us through telling us about the electrical work output and also the combined efficiency of the gearbox slash generator. Now let's write down the efficiency for gearbox generator, right? So as we said, the whole purpose of a gearbox or a generator is to convert the shaft energy, rotational energy of the shaft to electrical power output, okay? And the efficiency with which it converts the shaft rotational energy of the shaft to electrical power output is shown up as the efficiency of the gearbox slash the generator. Now we know the efficiency of the gearbox generator combo, and we also know how much electrical work output are we able to get from the turbine. So using this, we can simply calculate the work output of the shaft, which will be the electrical work output divided by the efficiency of the gearbox or the generator. So that's 375 kilowatt divided by 0.9, so 416.7 kilowatt. This is the amount of energy or the rate of energy that we are able to get at the shaft, at the rotor shaft. Okay. And this is the number that goes on to the numerator of the efficiency of the wind turbine formula. Now, all we need to do is to calculate the area. The area is simply pi d squared by 4. The diameter is known, 50 meter. The area comes out to be 1963 meters square. Now, it's just about plugging all of these numbers into the efficiency of the wind turbine formula right here. And once you plug all those numbers in, the efficiency comes out to be 0.354 or 35.4%, which is a very reasonable number. There are more efficient turbines available. We have reached efficiencies as high as about 50%, 45 to 50%, but 35% also is a very respectable figure. Okay, so that's the first part. Second part is to calculate the tip speed of the blade. So again, we have a wind turbine, right? And it has three blades. We want to calculate the speed at the step. So as we discussed before, uh, each blade tip it travels a distance of pi d, or the circumference of the circle formed by rotation of the wind turbine blades for every revolution, right? And therefore, we multiply this with the number of revolutions to calculate the tip speed. So it's basically pi d times n, and we have d. We have rotational speed also given to us. So it's simply a matter of plugging those numbers in. And when you do that, this rotational speed is given in terms of rotations per minute. So if you want it in terms of per second, you got to divide it by 60, okay, like we're doing here. So when you do the math, this comes out to be 65.45 meter per second. It's a very, very high speed, which is why tip losses are not negligible. They tend to be reasonably significant numbers, and that we need to consider and improve the design to minimize tip losses. So when you talk about 65.45 meter per second, it's basically 236 kilometer per hour, right? A kilometer per hour is a more relatable number, and you can see 236 is it's very, very high velocity that we're talking about, very high speed, right? It's faster than most cars can travel at. Okay, so this is the speed at for a wind turbine blade with a reasonable diameter rotor, right? 50 meters is not the it's not the largest diameter. We can have turbines of bigger diameters available as well. So this is a typical, again, this is not a very, very high tip speed. This is a very reasonable tip speed that you will find. Okay, moving on, we need to calculate the air velocity at the turbine exit at the Betz limit. So if the turbine was operating at the Betz limit, meaning if the turbine has an efficiency of 59.26%, if it had, then what would be the air velocity at the exit? So we simply calculated using the formula we derived for relating the turbine, the velocity of the turbine exit to the efficiency of the wind turbine, which is the V2 or the velocity at the exit of the turbine is equal to V1 times square root of 1 minus eta, or 1 minus efficiency of the wind turbine. Here we're taking it to be at the Betz limit. So the inlet velocity is 10 meter per second. The outlet velocity, if the efficiency is 0.5926, is going to be 6.38 meter per second. Now this is on the lower end, right? So if the velocity, the efficiency is 59.26, we can reach these numbers. But for our case, the efficiency was not 59.26. Our case, the efficiency was 34.5%. So if the efficiency is 34.5%, it means that we are not able to extract as much energy from the wind as we could in the ideal scenario, which basically simply means that the velocity at the exit should be higher than the ideal velocity, right? It should be higher than 6.38. So if you plug the numbers again, if you do it for 35.4% efficiency, you're going to get the turbine exit velocity of air at the turbine exit would be 8.04, or about 8 meter per second, right? As expected, higher than 6.38. Okay, so this is it. This completes the very simple calculation for the wind turbine. Now let's talk about an actual power curve. Let's look at an actual wind turbine and see how these numbers look at, and then we'll talk about the outlook of this overall technology and wrap up this chapter. Now, this is a very busy graph here. It's showing us the power output on the left y-axis, wind speeds on the x-axis, and the wind distribution on the right y-axis. So the wind distribution is simply telling us the probability of a certain wind speed existing, right? So this green bar graph that you can see here is showing the wind distribution at different wind speeds, right? So certain what is basically telling you is when you look at different wind speeds, the most probable wind speed is basically the one which is corresponding to this number. So it's around probably 3 or 2.5 is to 3, right? And as we go higher, as you go to higher and higher wind speeds, the probability of a turbine reaching those facing those wind speeds is lower. So basically, this is a very location dependent curve, and at this given location, looks like if you're at if you're talking about wind speeds of 10 meter per second, then the probability that the wind speed will be 10 meter per second is it's even lower than 1%. So it's a very small probability. Okay, so this simply gives us the probability distribution of the winds. Now, what we have now is also the power that is being produced. So we have two lines here. The black, the sorry, the dark blue line, the navy blue line, which is this one, it shows the power available in the wind. So it is basically simply a calculation of half rho a v cube, nothing else. Okay, this is the power available in the wind, and then the light blue curve is actually showing how much power we are extracting from the wind. So in the initial part, right? We are extracting reasonable amount. I mean, the wind turbine efficiency is reasonably high. You can see the difference between these two lines is very small. The difference keeps on increasing a bit, and eventually, basically, once it reaches higher wind speeds, we are not designing the wind turbine to operate at at very high speeds. So the wind turbine is designed to operate at certain specific speeds, and as the wind speed goes higher and higher, the using pitch control, we move around the wind turbine blades in such a way that we change the angle of attack so that we are not extracting all the possible energy from the wind. And this is simply because every wind turbine has a rated power, and although the wind may have more available energy, we don't want to extract all of that energy, right? We want to extract some of that energy. So what you will see is that the gap between energy available, which is this number, and the energy that we're extracting, it becomes higher and higher as we go to higher wind speeds, right? And eventually, we are basically uh, reaching a plateau in terms of how much power we are extracting. It is simply the rated power. Okay, the wind speed is higher than what we want, and we are still extracting from the wind, of course, but not very efficiently. And this is perfectly fine because if you design a wind turbine to operate at higher and higher loads, higher and higher wind loads, it's going to add a lot of cost. So we want to extract power, but of course we want to reach we want to extract a certain amount of power from the wind so that the stress levels and everything within the wind turbine design are manageable. Okay, so what you can see here is that the power curve, it follows the energy available in the wind at the beginning. So I'm showing it in red now. So this power curve, which is light blue, it follows the energy available in the wind initially, and then once the wind speeds reach a little bit on the higher side, then it stops following because now we start implementing pitch control as we discussed earlier in the class. And here it basically slows down, and we're producing still enough power, more power than we were producing at lower velocities, but we're now sort of approaching towards the rated power output of this wind turbine. And at 2.5 megawatt, in spite the wind speed going higher and higher, the output is flat, which means we're using pitch control and we're not extracting all the available energy, and which is perfectly fine. So this is how it would go on till a certain velocity of the wind, and once it reaches 20 meter per second, about 20 meter per second, then we have the cutout speed. So at this point, we completely move towards shutting down the wind turbine. So we don't want to generate any power when the wind speeds approach higher than 20 meter per second. So at this point, you can see we have applied the brake. The power output is absolutely zero. Okay, so the whole purpose of designing this power curve is to this power curve in combination with the wind distribution tells us how much energy are we able to generate, right? The power simply tells you what is the rate of energy generation. This is per second, but when you look at it over the period of a day, period of months, basically the wind distribution in combination of the power curve tells you, okay, how much power is available at for how much time, and you'll be able to calculate how much energy overall are we able to generate. And you want to maximize that as much as possible. So it makes sense to tune the power curve to the wind energy distribution at any given location as much as possible, right? And The reason is the wind turbines. Most of the wind turbines are designed to be very efficient at slightly lower speeds, slightly lower than 10 meter per second, simply because, as you can see from this, the wind distribution curve, most of the wind speeds are around 5 to 6 to 7 meter per second, right? That's where the majority of wind speeds occur. I mean, that's the most probable wind speed at this particular location. As you go to higher and higher wind speeds, the probability becomes lower and lower. So it simply doesn't make any sense to design a wind turbine to operate at very high wind speeds when you're not going to get that wind speeds very frequently, right? Again, all this discussion is very location dependent. If you have another location where the wind speeds are much higher on average, then of course you have to select an appropriate turbine. Okay. Another thing about the nomenclature of the turbine, most of the wind turbine model number tells you enough information about the power output and also the rotor diameter. So when you see GE 2.5 the 2.5 tells you the power output, the rated power output, which is 2.5 megawatt, and the next number 120 tells you the rotor diameter, right? So for this wind turbine, the its rotor diameter is 120 meters, or the rotor radius is 16 meters. Okay, so that's basically about it. Now, moving on to summarizing this chapter, well, in terms of utility scale wind turbines, we're going to see more and more of those. And the design that has won over and has become really common everywhere is the horizontal axis wind turbine, which is upwind, has three blades, and operates on pitch control. It is basically the wind turbine that you're seeing in the picture on the right. Okay, this is the exact wind turbine. This is what all companies are building. Now, what is the difference in what different companies come up with? Well, the difference among various industry players is simply in terms of the blade material that they select, or maybe the alloy, you could say, or more specifically, it's in the gearbox selection, basically design of the generator and overall controls. Otherwise, this is the overall shape is exactly the same. It's all horizontal axis, it's all upwind, it's all three blades, and all of them have pitch control. Now, to wrap this up, let's quickly look at what is in the future. Well, in terms of technology development, a lot of technology development is taking place in the wind turbine areas, basically in terms of capacity enhancement. So we are still going to taller and taller heights, larger and larger blades, simply to access more wind speeds to generate more power. There's also more efforts to increase the overall turbine efficiency, to enhance it through using advanced control methods such as individual pitch control, more smart blades with control surfaces, built-in sensors, and site-specific designs, right? So as we discussed in the last one, based on a given site, you need to have the power curve of the turbine tuned to it so that you can maximize the energy output from that particular site. So site-specific designs are becoming more common, and of course, farm level optimization. You have to optimize the distance between different wind turbines and how you arrange the wind turbines in a given wind turbine farm. This is something that you'll also do in your assignment. You'll not do the optimization. You'll just see, okay, what is the sort of arrangement that is typically used, right? Using the software as the SAM. So this is part of your assignment for which you'll be doing. So what about smart blades? This is how a smart blade looks like. This is from Purdue, and they are a lot of people are working on these smart blades to give us more specific control to make things to overall increase the efficiency of the turbines. Right? There are other directions where things are moving. Weight reduction, certainly through advanced materials, direct drive systems. Offshore wind turbine, this is already picking up. Will require improvements in foundations, construction, and so on. There's also some multi-rotor systems coming up, such as the Vestas multi-rotor system shown here in this picture. You can see it's one tower holding four different turbine blades, reduces your capital cost per turbine blade or reduces your capital cost per kilowatt hour. Um, you also have airborne wind energy, another kind of fancy technique, which people are exploring. So a lot is happening in this space, and it's something that's worth looking at. Through this a detailed chapter on wind turbine energy. I hope you have learned the basics and you have enough confidence to understand the industry terminology and to understand the power curve for different wind turbines. So that's it for me here. We'll move on to the next chapter in the next class.